All right, guys, welcome back to the last video in this segment. This will be on a topic called continuity. So much like a lot of topics in calculus, we can get very in-depth on this. Again, I try to keep things pretty simple. This will pop up throughout the year. It's used in a lot of definitions. You have to reference it when you're doing free response later in the year. Um, we'll get into two definitions here essentially for continuity. One is just kind of like the you can wrap your brain around it definition. And the second one, we'll get into a little more math-based definition. But essentially, continuity is you having the ability to go from just real simple, from A to B, whatever that might be, from A to B without lifting your pencil. So if you can think about what I'm trying to describe in a graphical sense, if you can go from point A to point B and you get there without lifting your pencil, you get there in one smooth connected line or curve, then that is called continuity, or it's continuous, depending what form of the word you're using. Um, so we're going to have to look at counterexamples to show when something is not continuous. Continuous just means it is smooth, it is connected, there's no interruptions in the graph. All right, so what does that actually mean in terms of a math definition? Well, the first thing is pretty simple. F of x, your graph, we're going to say it's defined at so in this definition, we're going to be looking at, is it continuous like at a point, at a specific area? It's defined at, we'll say x equals c. And c is going to stand for whatever constant, whatever number I'm interested in. So is it defined at, pretend this is like 3 or 4. So the graph has to exist at that spot. Okay, the next one is the limit as x approaches c from the left has to be the same as the limit as x approaches c from the right. And now let's start looking at counterexamples. So in other words, if we look at the broken ruler graph, in this case, the limit as we approach, we'll say we're looking at 0 in this case. As we approach 0 from the left and right, those limits do not agree. This one would be 1 and that one's -1. So since those limits don't match, it would not be able to be defined as continuous. So because again, something that's continuous, we can go from A to B without lifting your pencil. It would be smooth and connected. All right, and finally, there's a third rule for continuity, and that's the limit as x approaches c must be equal to f of c. So let's go check out an example over here. And let's say that you have this for a graph. So we'll just call that c. So the limit as we approach c from the left and the right, that's both 1, right? As we approach c from the left side, it's 1. C from the right side, it's 1. So that sure sounds like rule number 2 is in good shape. But now let's take a look here. This is clearly not continuous because you could not have made this whole graph. This is a closed dot up here. This is an open one. We could not have made this whole graph without lifting our pencil. So does the limit as x approach c equal f of c? Well, f of c is equal to 3. But the limit as x approaches c, that's going to be 1. And since these two things aren't the same, then this would be not continuous. So in order for it to be continuous, these two things have to be the same. Example, if we have a graph that's smooth and connected, so here we are at c, we'll just say that's 2. As you approach c from the left and the right, you come up with 2. What is f of c? F of c is also 2. So hopefully that kind of makes sense in a mathematical sense that in order for something to be continuous, it has to be defined at the value you're interested in. The limit from the left has to match the limit from the right. And the limit as you approach it has to be the same as the function value at that spot. Okay. So I'm just going to show you guys a handful of things that they will ask throughout the year. A popular one is, let's say, a question that says find the value k that would make f of x continuous. All right, and let's say that we have the following piecewise function. F of x is equal to, and we'll say 2kx squared plus 5x. And that is good for when x is greater than or equal to 2. And 2x minus 3, and that's for when x is less than 2. So we have to make sure we understand how to read a piecewise function. You have this gibberish whenever it's greater than or equal to 2, and you have this stuff whenever it's less than 2. And we want to know what value for k, here's k right here, would make all of this continuous. So at first glance, you're kind of like, what are we talking about here? But then when you kind of map it out, I tell people to understand what's going on. It's all surrounding x being greater than or less than 2. So here's what I would tell people is that this top graph is for when it's greater than or equal to 2. That's everything happening in that direction. And this bottom one is when it's happening everything in that direction. So could we actually try to map all this out? It kind of, but all you need to know is that when it's less than 2, it's that red graph. And when it's greater than 2, it's this black graph, just totally making this up. And if we want it to be continuous, well, what do we know has to happen at 2? The red graph and the black graph have to be exactly the same value. It has to connect somewhere in order to make this continuous. So in other words, we would need this top equation to be equal to the bottom equation. So let's try to do that. 2k x squared plus 5x is equal to 2x minus 3. And what do we know about this whole problem? It's when x is 2. So we can put 2 in for the x's. So this is 2k 4, 2 squared, plus 10 equals 4 minus 3. Well, 2 times 4, that's 8. So 8k plus 10 is equal to 1. 8k, I'm going to subtract the 10, is negative 9. Divide by 8, and k is equal to negative 9/8. So if you plug in negative 9/8 for k, it should make this top and bottom line equal to each other when x is equal to 2. Now, obviously, this drawing isn't quite accurate because it ended up being a negative number, so they would be meeting somewhere down here. But the visual gives you an idea, hopefully, of what the process is. So if you're looking for this value, you'd be setting the top equal to the bottom, plugging in the x value, and solving for k. Okay. So now, if something is not continuous, we also need to explore what that means. So everything we looked at so far was continuous, continuity. The opposite of that is if something is not continuous. Something is not continuous. There's 3 main situations for that. The first one is called a jump discontinuity. And essentially what that means is there's a jump in the graph. So go back to our broken ruler, the 2 of them going either way. A jump discontinuity essentially means the limit as x approaches c from the left does not equal the limit as x approaches c from the right. We can have something called an infinite discontinuity. And that involves things that are headed to infinity. So whenever you have things headed to infinity that are causing breaks and jumps in the graph, that is called an infinite discontinuity. And the last one is the one we'll focus most on. That is called a removable discontinuity. All right, and a removable one, there's some algebra we can do with that. So for a removable discontinuity, that's something that looks like this. We have a graph and we have a open and a closed dot. So now while this is not continuous, we could fix this to make it continuous. If there was a way to pick up this closed dot and throw it into the open dot, then this whole thing would then become continuous. And that's what we're going to look at. So if I gave you the following problem, if we said f of x is equal to x squared minus 9 over x minus 3. And we're going to say, again, this is a piecewise. So this is for when x does not equal 3. And when x does equal 3, we'll say that it's equal to, who knows, whatever, 10. All right, and we're asking, is this continuous? And if it's removable, could we fix this situation? So let's do a full exploration on this. This one would factor, right? So this is really going to be x plus 3, x minus 3 over x minus 3. So that creates a hole in the graph at 3. And what are we left with is x plus 3. So the graph that this actually all represents is the graph of x plus 3. Well, what's the graph of x plus 3 look like? It has a y-intercept at 3, and then it goes up 1 over 1, up 1 over 1, up 1 over 1. By the time you get to 3, you're at 6, and we just said there's a hole in the graph there. And what does this tell us? When it's 3, we have a closed dot at 10. So there's our graph of what this is. And now we're asking, is there a way that we could remove this discontinuity and rewrite this? And the answer is yes. So to do that, we write capital letter, whatever this was, and we're going to write a new function. So it's capital F of x is equal to. So anywhere that it was not at 3, did we have a continuity problem? In other words, like at -1, -2, at 0, 1, 2, 4, 5, 6, 7. Nowhere else did we have a continuity problem. It was continuous, 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 continuous. Wait, we got a problem. Continuous, continuous, and so on. So we can say that it was the old graph that we started with, little f of x, anywhere that x is not equal to 3. And then when x is equal to 3, well, what do we want this situation to be? We don't want it to be 10 anymore. We want it to be 6. And that piecewise function is a continuous version of the one we started with. This is called removing the discontinuity. Okay. All right. Now, another question you might have, is there a way we could have come up with this number 6 if we did not have this visual here whatsoever? And the answer is yes. After you factor cancel, take your x value and plug it into whatever's left. And that will spit out the value that you should be at. So if you don't want to make the graph of that whole thing, I'll show you another example in a second. You can just plug the x value into what's left, and that will get you what you're looking for. All right, so let's look at one more. If we said f of x is equal to, we're going to make a piecewise again, and let's say that we have 3x squared plus 6x over x plus 2, and this is for x is not equal to -2, and then we have 5 whenever it is equal to -2. Okay. So I'm going to encourage you to pause the video, give this a try. So this is a removable discontinuity. Go ahead and pause the video and try it. See if you can come up with a piecewise function that would then make this continuous, and then hit play when you're ready. Okay, so what should we be looking at here? We should factor this. So this factors into 3x, and then that leaves you x plus 2 over x plus 2. Hopefully that makes sense to say that cancels and creates a hole in the graph at x is equal to -2. So you could graph this out if you chose to, no problem. I'm going to go skip ahead here and just say capital F of x is equal to, and it's going to be the lowercase f of x whenever x is not equal to -2. And then when it is equal to -2, all right, we're trying to figure out where it should be to fill in that spot. And that would be at -6. Okay. Um, so how did I get that? Plug the -2 in to the 3x, or you could have visually had a graph going. If you graphed 3x, you would come up with the same thing. You would see it visually. Okay? And again, that is called removing the discontinuity. So in terms of what you're going to work with in calculus for continuity, I mean, that's a very big portion of it right there. There's little nuances that pop up throughout the year that we'll go over. But if you can make sense of this video, I mean, that's 80–90% of what you need in calculus for continuity. So hopefully this makes sense. And I will see you guys soon.